Hello, this is Madam Lee again, and in this video, we are going to apply the similar area ratio formula that we have learned previously to example 1 all the way to example 5. Okay, so very important condition before we can use the formula that we have learned previously is that they must first be similar figures, okay, or solids. So they must the question must give you the condition that they are similar. So now let's look at example 1. In example 1, we are given two figures, and it says that there is a smaller trapezium and a larger trapezium. So it is also given that the two figures are similar. So in this case, we can apply the formula that we have learned previously to find the area of the larger trapezium. So the area of the larger trapezium over the area of the smaller trapezium, okay, can be written as equal to 3 over 2, okay, the corresponding length squared. Okay, so to find the area of the larger trapezium, we can now multiply both sides by 16 to obtain the final area of 36 cm squared. Okay, so this is for example 1. Now let's look at example 2. Find the length of the larger cross given that the two shapes are similar. So again, we are given the condition that they are similar. So again, I can apply the similar area ratio formula onto this question. So to find the larger length, we are given both the area. So I can use 75 over 192 equal 6.5 over the length that we want to find squared. Now, it is okay to put 192 first instead of 75, but just make sure that if you have decided to put the smaller area first, then you have to standardize by putting the smaller length on top as well on the other side of the equal sign. Okay, so they must be matching. In this case, I need to look for the length L, but I'm very aware that there is a square that is outside of this bracket. Now, there is more than one way to simplify this equation, but I'm going to go with square root both sides. Okay, so that I no longer have the square outside the bracket. Now, when we square both sides, we usually will put a plus minus, but in this case, we do not have to because the length ratio, both are length, so it should give us a positive ratio on the other side. So because of the square root, we can calculate square root 75 over 192, and you will get the value 0.625 equals 6.5 over L. Okay, so you can do a simple cross multiplying and simplify to get the length to be 10.4 cm exactly. Now let's look at example 3. In example 3, we are given that ABC is similar to the larger triangle ADE. Okay, so whenever they say that the figures are similar, okay, one tip to see the shapes clearer is actually to redraw the shapes so that later we can identify the similar figures clearer. Okay, so they say that these two are similar. It says that AB is to BD is 3:1. It means that on my separately drawn triangle, AB is 3 units and AD, which is the bigger side, altogether, it's 4 units. Okay, so they also say that AC is to CE is also 3:1. So AC to CE is also 3:1. Now notice that Madam Lee did not use the same symbol. So here I use a circle for the 3 units. Here I use the triangle for the 3 units because they did not tell me that AB is exactly the same length as AC. So these 3 units, it may not be the same 3 units. Okay, but comparably, the one with the circle are the ones that are comparable, and the one that are the triangles are the one that are the comparable 3:1. Okay, but okay, let's see what we need to do with the ratio there. It says that the area of ADE is 32 cm square, and we are supposed to look for the area of the trapezium. Okay, now in this question, what is similar is the triangle, not the trapezium with the triangle. So to obtain the trapezium, we can find the smaller area of ABC and do a subtraction with the larger area of ADE to obtain the trapezium portion. Okay, so let's look for the smaller area ABC first. So to look for area ABC, because they are similar triangles, I'm going to use my similar area ratio and take a corresponding length, 3:4, put a square. And therefore, I can find the area of ABC to be 9/16 times 32, which is 18 cm squared. Okay, so after finding the area of ABC to be 18 cm squared, I can now take the larger triangle area minus the smaller triangle area to finally get the area of the trapezium. Okay, so the area of trapezium BCED is therefore 32 minus 18, which is 14 cm squared. So this is the final exact answer. Okay, so please note that, okay, so this is a possible error, okay, that is quite common in finding the area of the trapezium. Okay, even though you are given the area of the larger triangle of 4 units in total, we do not square the 4 units from the larger triangles to 1 unit of the trapezium. So this is not a correct concept. Okay, so there's nothing we can do to the 1 unit directly because the trapezium is not of a similar figure to any of the triangles that we are referring to in this question. Okay, so we have to go with the way of talking about the similar triangles first, finding the area of the similar triangle first, and do our subtraction to get the trapezium. Now let's look at example 4. In example 4, we are given that the two cylinders are similar. Okay, so this is a keyword. And we are supposed to link up a relationship between A, B, P, Q. So if you look at what is A, B, P, Q, they are, AB is the corresponding height of the similar cylinder, P is the total surface area of the smaller cylinder and Q is the total surface area of the larger cylinder. So since they say they are similar, I'm going to now link them up using the similar area ratio that we have learned in page 1 and 2. So I can write this down, P over Q, the smaller area over the larger area is A over B squared. So please check that they match. So P is the smaller cylinder area and A is the smaller cylinder's height. So please just look across the equation to make sure that the smaller one, if you start with the smaller one on top, you start with the smaller one on top of on the other side as well. Okay, so the question says make P the subject. So I have to remove the Q by multiplying Q on both sides. Okay, so I can now write as A squared over B squared, the expansion of the bracket with the square, multiplied by Q. So therefore, this is already making P the subject. Now let's look at the last question for applying of our area ratio. In example 5, we are given that BC is to CD is 3 units to 2 units. Okay, and we are asked to look for area ACD given that ABC is 48 cm squared. Now, if you look at this question, the two triangles that are mentioned in the question, they seem to be different from our previous example. Okay, so the hint here is, are the two triangles similar? If yes, we can apply our similar area ratio, but if no, we cannot do that. So are they similar? If you look at how ABC is an acute triangle and ACD is an obtuse triangle, meaning there is an obtuse angle, the answer is no, they are not similar. So I cannot use the similar area ratio formula that we have learned directly. So in this case, what else can I do to be able to find a relationship between them? Okay, because obviously the ratio is trying to link up a relationship between them, and the fact that they give you just the bigger the area of ABC also means that there is something that we can link up over there. Now, if you look at how the two triangles are side by side, and not only that, they start from the highest same point of A, and if we drop down a height from A all the way to the base, the base is what we call a shared base, and this height is also what we call a shared height, because for A, B, C, the height can be seen as the red color H, and for the obtuse triangle ACD, this height H is also its height. So in this case, we can form an area ratio in this manner. Okay, what we want to find is area ACD, and we are given area ABC. But over here, I'm not going to do what we have done previously. Okay, so because they are not similar triangles, I'm going to go with the most manual way of finding area of a triangle. So area ACD, I can write the area as half times base CD times the shared height H. And 48 cm squared, in the most manual way of finding area of triangle, I can write it as half times base BC times this common height H. Now, if you notice how the h is common, we can now divide half from both the numerator and the denominator, and h from the numerator and the denominator. Okay, so what we are left with, CD over BC. In this fraction manner, we can apply the ratio that is given here, 2 over 3, to represent the ratio of CD is to BC. So, in summary, whenever you have two triangles sharing the same height and the same base, there is actually this simple relationship that can be formed using just half times base times height over the other half times base times height. And because the height is the same, they get divided away. So therefore, the area ratio of ABC is to ACD is basically just the ratio of the base of the two triangles. So now to find area of ACD, I can multiply both sides by 48 and simplify to get, therefore, the overall area of ACD to be 32 cm squared.